All right, in this series of lectures, we're going to begin the topic of the exterior calculus and algebra. I don't know how far we'll get through it all. I don't know how far we need to get. We definitely need to cover the exterior calculus pretty thoroughly. And it's related very closely to the algebra. The algebra's got some interesting advanced topics in it. But to begin to study the exterior calculus, we need to discuss the concept of n-forms, because n-forms are the basic elements that are used in both the exterior calculus and the exterior algebra. And n-forms begin with zero forms. And zero forms are simply functions on the space-time. So f of x is a zero form. And remember, we have a space-time with a coordinate system, right? We've established a coordinate system on our space-time in 4 dimensions. And so f is a function of x0, x1, x2, and x3. So the partial derivatives of f with respect to any of those exist. We presume f is smooth enough that these partial derivatives always exist. So a zero form is simply a function on the space-time, and it really is it's a degenerate form of the n-form, so it doesn't have any unique, it doesn't exemplify any of the important properties of the exterior algebra, exterior calculus, but it is a place where we have to start, because we are going to introduce an operator d, and d, we are going to learn, is called the exterior derivative. And it's going to be a very interesting animal. We'll spend a lot of time talking about it. But the exterior derivative of a zero form can only be understood through definition. You have to just define it. And the exterior derivative of a zero form is going to be given by the partial derivative of f with respect to xi times d xi, where this guy is the basis of v star, which of course is just the basis of covectors, and of course it's all in the coordinate basis, just as we've talked about before. So now we have a definition of the differential of a function. We call that the differential of a function, or df. It's also the exterior derivative of a one form. We'll approach that idea a little later, because we've talked about two types of derivatives. This is the third one. This is the third one, so we're going to have to spend a little bit of time focusing on that. But we know what a zero form is, and we know what a one form is. So now, with this idea of a one form, we can talk about the one form. It's still a map. This is a covector, right? So it's still a map. In fact, it is a 0-1 tensor. I guess we've been doing it this way, 0-1 tensor. And it will act on a vector v, and it does so in exactly the way it always would, which is df dxi, comma, let's say v j partial j, which is partial f partial xi v j delta I j, which is partial f partial xi v I, right? Which is really the same prescription as we've done before. And this has a bunch of different notations, right? So this could be partial I f vi, like that, or it's f comma I vi, right? We had that common notation for d by dxi of f is f comma I, right? That was another sort of abbreviated notation. I prefer this, actually, f one line I, where the covariant derivative, which we discussed before, is 2 lines, like that. I prefer those lines as opposed to the comma. Anyway, so that is our one form. That is our one form. Okay, so now we are going to begin and we're going to talk about n-forms. And as our example, I'm going to show what we mean by two forms. We already know what a one form is, which was a covector, and we already know what a zero form is, which was a function on the spacetime. So the place to start with I want to talk in detail about two forms, of course, but as we do it, I kind of want you to think about what an n-form is. But all of these guys are 0 n tensors. An n-form is definitely a 0 n tensor. A two-form is a 0-2 tensor. A one-form is a 0-1 tensor, which is also known as a covector, which is an element of the dual vector space. And a zero form is a 0-0 tensor, which we have also known as a function, which is usually given as an infinitely differentiable function on the space-time. Right? So n-forms, two forms, one forms, all of these are tensors, and they're members of the respective tensor product spaces. And a two-form is certainly a member of the 0-2 tensor product space, and as such, if the basis of the underlying vector space is E mu, the basis of the two forms is going to be E nu. And that basis is going to have the relationship that we've always expressed with this stuff. E mu, E nu is delta nu mu. We're going to be reviewing a little bit of this now. It's been a while since we've literally done the straight up tensor calculations, but that thing is going to equal that thing. And in the coordinate basis, we now have dx mu partial nu, but it still is defined the same way. So this is just the coordinate basis expression of this, and this we are now understanding as a one form, which is the one form where df, instead of an arbitrary function, we just put in the coordinate function x mu. Could be x1, x2, x3, whatever. But we're now understanding this as a one form, which of course makes perfect sense because it is a covector. So with that in mind, we now explore what a two form is. A two form, we've already said it's a 0-2 tensor, and the reason I'm saying that a few times without zeroing in on why a two form is a special kind of 0-2 tensor is I want to emphasize that all the machinery we've built to understand how these things operate, and for example, what I've just written right down here, that is all in effect. It's all just a special application of stuff we already know. We're just going to add a slightly new layer of constraint, and then with that constraint, we're going to drop down another layer of abstraction. So let's start with the constraint. As a reminder, what any 0-2 rank tensor, if a two form is a 0-2 rank 0-2 tensor, that means necessarily that we must, whatever it actually is, we must be able to express it. Let's say the two form itself we call omega. We must be able to express omega as in the following way: omega mu nu dx mu dx nu. It has to be expressible like that, where this is the basis of the tensor product space, the 0-2 rank tensor product space, and these are the components of that on that basis. And it's a double sum, but it's still a vector space. It's the tensor product space exactly like we've ever learned. In fact, it's very important now that we look at what it gobbles up, right? It's looking, because it's a 0-2 rank tensor product space, it's looking for two vectors, which I'll call V delta partial delta and W lambda partial lambda. So it's looking for two vectors to eat up, and I've written the vectors again in the coordinate basis in their component form. And we know that this is going to end up being, and I'll just work it out because it's been a while since we reviewed it, omega mu nu, that component, the linearity allows us to pull out these components here. So I get V delta, W delta, and then what's left behind is dx, is the actual tensor basis, dx nu, operating on delta oops, lambda, like this. And we know that this is a mapping, and we know exactly how that mapping works on the components of the dual basis. And so we can replace that right away with dx mu partial delta, dx nu partial lambda, and we know that that is delta mu delta and delta nu lambda. And therefore, with these delta functions, with these two delta functions here, we can go up to here, and I think what I'll do is I will change the subscripts on the omega, and I will get mu becomes delta, so I'll go omega delta lambda v delta w lambda, like that. Okay, so that is just sort of a review of how a 0-2 tensor maps two vectors into a real number, because that is clearly a real number. It's a double sum, and just as a review there, so omega 1 1 whoops omega whoops 1 1 v1 w1 plus omega 1 2 v1 w2, etc., etc., etc. So it adds it all up. Now, what is it that distinguishes this a typical routine everyday run-of-the-mill 0-2 tensor like we've been discussing from a 2 form? And the difference is that there is a constraint added. And that constraint is that we are seeking antisymmetry. We are seeking tensors of the form where the tensor acting on two vectors, v and w, the real number it produces is opposite of the real number it produces when it acts on w and v. And this constraint, a 0-2 tensor that follows that constraint, is called a 2 form. It's a 0-2 rank tensor. Of course, we know that because it's gobbling up two vectors and it's giving us a real number. So we know it's a 0-2 rank tensor. And it's a 2 form because it is it's antisymmetric in the vector arguments. And so we can flush this out as to a constraint on the components of a 2 form. We already know that the components of this guy we called mu nu, and the attached basis vectors was like this. And so we now can turn this rule into a restriction on these guys. And it's not very hard to see, because what we're looking for is this has to equal the opposite of omega mu nu dx mu tensor product dx nu on this. And we know the first one already. We know that this is going to be mu nu v mu mu, what did we say it was before when we did it? We came up with delta lambda. Okay, so it's delta lambda v delta w lambda. If we reverse these two, so now we have w lambda partial lambda v delta partial delta, and we put those in here like this, what we're going to do is we're going to end up with the opposite delta functions. We're going to end up with w lambda v delta, but the delta functions are going to switch, and we're going to get mu lambda delta nu delta. So we're going to get, and if we impose that on the component, we get minus omega lambda delta and V delta W lambda, where I just flip these two in order to make it look the same. Because the next thing you see is this cancels with that, and the final constraint ends up being W delta lambda equals minus W lambda delta. And that's the constraint on the coefficients that force the antisymmetry of the tensor. Now, when you study general relativity in the beginning, and they define an antisymmetric tensor, remember, they don't even play around with these guys. So this is where they start with their definition, right? They just say, oh, you flip the two indices, and they should flip the sign. What this literally means is that omega 0, 0 equals minus omega 0, 0, right? Because you flip 0 and 0 to 0 and 0, you still, the rule is for all possible flips. Well, you can flip two zeros, so you need to get that. And then you need 0, 1 equals minus 1, 0. Omega 0, 2 equals minus omega 2, 0. Omega 0, 3 equals minus omega 3, 0. All the way to omega 3, 0 equals minus omega 0, 3. And which is sort of, I mean, there's a lot of redundancy when you write it this way, but it goes all the way to omega 3, 3 equals minus omega 3, 3. And so what does this tell us? Well, we definitely know that in order for a number to be equal to its own, equal to the opposite of itself, this means that all the diagonal elements must be 0, right? So omega 3, 3, omega 1, 1, omega 2, 2, omega 0, 0, those are all gone. And then all the other components are just of opposite sign. So with this constraint, I can now write a very general form of a 2 form. I can write a 2 form in a very general way using this constraint. And I'm going to do this in sort of this full, long glory, and I have a reason for doing it all out. So I'm going to do this all out, and I'm going to write the most general 2 form. So the most general 2 form. Omega will be our 2 form. And I know that the 0, 0 component doesn't exist, so I'm going to start with omega 0, 1. Omega 0, 1 will be multiplied by dx 0 tensor product dx 1. And then I would want omega 1, 0, but I know omega 1, 0 is minus omega 0, 1, so I just go minus dx 1 tensor product dx 0. And that combines 2 of the basis vectors, right? This is a basis vector of the 0, 2 tensor product space, right? So any 2 form is an element of 0, 2, the tensor product space of 0, 2 ranked tensor. And this is one of those basis vectors, and this is the other basis vector. The component of this basis vector is minus 0, 1, which is what we expect, because the component's supposed to be 1, 0, but we know 1, 0 is minus 0, 1. So this is completely fine, just to put the minus sign there and distribute this constant. And then this is the basis vector, this is the component, by definition, of this basis vector. So the antisymmetry constraint allows us to sort of blend these 2 basis vectors together. Then that plus omega 0, 2 dx 0 dx 2 minus dx 2 tensor product dx 0 for the same reason, plus omega 0, 3 dx 0 tensor product dx 3 minus dx 3 tensor product dx 0 plus, now what? Omega 2, whoops, omega 1, 2, right? Omega 1, 2. Omega, we're not doing omega 1, 0 because omega 1, 0 is already accounted for here. So we're doing omega 1, 2. And that'll be dx1 tensor product dx2 minus dx2 tensor product dx1 plus omega 1, 3 dx1 tensor product dx2 minus dx3 minus dx3 tensor product dx1 plus omega 2, omega 2, 0 is already accounted for here. Omega 2, 1 is already accounted for here. Omega 2, 2 is 0, so omega 2, 3 dx3 tensor product dx2 tensor product dx3 minus dx3 tensor product dx2 plus omega well, I think that's it, right? That's it. Omega 3, 1, 3, 0, 3, 1, and 3, 2 are all accounted for, and 3, 3 is 0, so we don't even need any more. So this covers everything. So understanding that all the diagonal terms are 0, this is the way to write the most general 2 form. And we have 1, 2, 3, 4, 5, 6 different numbers to establish what that general 2 form is, instead of what we would normally expect for a 0-2 tensor, which would be omega mu nu e mu tensor product e nu, which would be 4 times 4, which would be 16 separate numbers. So 16 separate numbers have dropped down to 6. And we actually have all 16 basis vectors are accounted for, right? We got 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus the 4 that are 0, that makes 16. So this is our form for the most general 2 form. But you know, it's hard to argue it's a big deal, right? This is just an antisymmetric 0-2 tensor, right? That's all we've actually done. And just the antisymmetry itself has given us a bunch of constraints that has driven us to this form. So if we were only dealing with antisymmetric 2 tensors, maybe it'd be nice to have a way of capturing the fewer components that you need. By the way, I haven't talked about why this is important, right? We haven't even gone near why antisymmetric 0-2 tensors might be important. That's coming later. We just have to understand what the construction is right now. So what we would like to do is have a little tidier construction for this. And I'm going to propose one, and it looks like just a notational, the way I'm going to propose it, it looks like just a notational convenience, but it's actually a very profound change. What we're going to do is we're going to define a new operator between one forms. And that operator is going to be called the wedge operator, the wedge. And the wedge operator of 2 vectors, or I should say 2 one-forms, say dx mu dx nu, is going to equal dx mu tensor product dx nu minus dx nu tensor product dx mu. And with the wedge product, I can now write omega as omega mu nu dx mu wedge dx nu. Almost. I can almost do this, right? Clearly you can see how this is just shorthand for these, right? So that's kind of good. This is, it's really meant, you could almost think of it as a pure straight up substitution, right? Pure straight up substitution. But the way it's written is very suggestive of a new vector space where this is now the basis. And instead of having 16 basis vectors that all look like variations on this, we only have 6 basis vectors, which are all written this way. So that's important. However, there's still 10 of these guys, right? So there's too many of these for 6 different basis vectors. And also there's the problem of what about dx nu wedge dx mu, right? So there's something going on there, right? We would have to include all of those, but we really haven't included all of those here, right? We only have one of them. We don't have x3, x2 minus x2, x3, which is what we would have to have for this whole form to make any sense. So what we do is 2 different things. First, we write this with a little, let me erase this and show you how we actually write this. We write this mu nu with these little lines here. And those little lines mean that mu is always less than nu. And that cuts down the number of components. And that's exactly what we have here, right? If you look, the first component is always less than the second one. And so with that restriction, now this actually captures this whole collection of components. And it does still look like a little bit of a vector space. So that's one interesting thing. But there's another way of looking at it still. We know that dx mu wedge dx nu, we know that that equals this right here. And we know that if I flipped it and I wrote dx nu wedge dx mu, what would essentially happen is this term would show up here and this term would show up here. It would just reverse them, and all that is a sign change. So we're led to the principle that dx mu wedge dx nu is minus dx, well, let me exploit the full power of this pad. It's equal to the opposite of the swap, right? It's antisymmetric, right? This thing is antisymmetric in the 2 terms, right? It's when you switch the 2 terms, you flip the sign. So with that in mind, we don't need to necessarily do this and keep this tricky ordering. But what we need to do is realize that if we write omega equals omega mu nu dx mu wedge dx nu, if we keep it this way and we allow mu and nu to run over all the indices, we're going to capture 1, 2 and 2, 1. So we know the sign will flip. The sign will flip here, but the sign will also flip here because we're going to flip the mu and the nu here as well. So basically we're going to double count is what it comes down to. And by the double count, to compensate for the double count, all we have to do is divide it by 2. And so there's 2 ways of writing the most general form of a 2 form. One is omega equals omega mu nu with these little bars, dx mu tensor product dx nu, and the other is 1/2 omega mu nu dx mu tensor product dx nu. And I've seen both in textbooks, right? I see both methods. And we're going to generalize this soon, but this is for 2 forms. So that is an important way of understanding how to write down the most general 2 form. Now about this wedge product, this is something we need to learn a lot about. Right now I've written the wedge product in between these basis vectors of the covector space, or between essentially these basis 1 forms, right? These were the basis 1 forms. But the wedge product can take any 2 1 forms, the way we're defining it. So I can have a 1 form that's A mu dx mu, wedge product B nu dx nu. And if I treat that exactly the same way as A mu dx mu tensor product B nu dx nu minus B nu dx nu tensor product A mu dx mu. Well, I know all about tensor products, and I know that they're linear, so I know that I can take this and write A mu B nu dx mu tensor product dx nu minus dx nu tensor product dx mu, which of course is A mu B nu dx mu wedge dx nu. So I've basically shown that first of all, I've shown that this wedge product makes perfect sense in the context of any two one-forms, right? Not just the basis one-forms, right? That's one thing. I've also shown that it's linear in these arguments, right? That if you have the scalar multiplication inside these one-forms, so now say I have two one-forms, omega and gamma. Say these are one-forms. So meaning I could substitute omega mu dx mu gamma nu dx nu if I wanted to. But I'm just going to leave it as omega nu. So if I wrote omega wedge product gamma, that makes perfect sense. Because these are both, if omega and gamma are one forms. Because right now I'm only talking about the wedge product in terms of one form. So given that, I could also say if I take a scalar and multiply by omega, say the scalar is A, so A omega wedge gamma is equal to A omega wedge gamma, like that. And likewise with the gamma. Another thing that's important to show, so I've got this ability to handle scalars. Another thing that's important to show is if I have a one-form omega, a one-form gamma, and a one-form beta, omega plus gamma, that's a one-form, right? That's a one-form because it's a covector plus a covector, which is another covector, because covectors are in a vector space of covectors. So what about that with a wedge product of beta? Well, I can break this whole thing out, right? And I can say, well, this is supposed to be omega plus gamma, tensor product beta, plus beta, tensor product omega plus gamma, right? But I know tensor products are linear, right? So I know that this is going to be omega tensor product beta plus gamma tensor product beta plus beta tensor product omega plus beta tensor product, oops, I put pluses in there. Why am I putting pluses? The whole point is that it's a minus, right? And then therefore this will be a minus 2, minus beta tensor product gamma, which this minus this is omega wedge beta, and this minus this is gamma wedge beta, right? So I now have a way of, I've now shown that we have this additive property based on the definition. We can add these things together like this. So we have a scalar multiplication ability, right? And we have this additive ability. Now the additive ability should be no surprise because omega wedge omega wedge gamma is a 0-2 tensor, right? It's an element of the rank 0-2 tensor product space. So you should be able to add it without any trouble to any other element of the 0-2 tensor product space. So delta wedge beta is also an element of that. You should have no trouble adding them together. They're vectors in the sense. A little less obvious is this question, omega wedge omega, which by our strict definition of how we've constructed the wedge product should be omega tensor product omega minus omega tensor product omega, which is obviously 0 by design. Well, not by design. It's 0. It's mathematically 0. It'll always be true for any one form omega. So any one form wedged with itself will always be 0. And this is a good way to see the antisymmetry of these things, because I could write omega plus gamma wedge omega plus gamma, and I could immediately see that that's going to be omega wedge omega plus gamma wedge omega plus omega wedge gamma plus gamma wedge gamma. So I know this is equal to 0 because that is the same as that, and we already have the rule that any two, this is a one form and that is a one form. It's the same one form, and the same one form with itself is always 0. So I can put 0 over here. And I also know that that's 0 and that's 0 by the same rule here. So I end up with gamma wedge omega equals minus omega wedge gamma. So this wedge product, if you flip the operands or the arguments, you flip the sign of the whole thing. And so that's really important, right? So, but that we've already sort of figured that one out. But the point is it's a result of this thing. And the reason I've gotten omega wedge omega equals 0 is based on this definition that I've been using. In a more sophisticated treatment of this, you actually start with this as an assumption. This is motivated. You want this property. And from this fact, then you prove the antisymmetry. That means if you have something a wedge product that has this product, that has this property of any one form wedged with itself is 0, you're forced to get antisymmetry out of it. So we'll take that approach later. But right now I'm just going off of the basic definition that we've used previously.
Now you may be able to see where all this is headed, but we've already shown that the wedge product of any two one forms is an element of the 0-2 tensor product space, but not just any element, it is an antisymmetric element. And we've seen how that ultimately forces itself as a condition upon the components, right? So this being an element of this ultimately can be written in some form mu nu dx mu dx nu. And now we understand that the most general tensor, the most general antisymmetric tensor always has these guys essentially almost as a basis, right? You see that they have to appear in these 6 forms, which is less than the total number of allowable forms, which would be 16 if it was in a general second 0-2 rank tensor. There'd be 16 different basis vectors, of which 12 are depicted here and 4 were 0. So if we think about these in this form a little bit, we realize, there is the possibility of understanding all the antisymmetric tensors of this tensor product space as its own vector space with its own basis that actually has a smaller dimensionality than 16, which is what we expect from here. Now, the reason this R tensor product space or R02 tensor product space has a dimensionality of 16 is because we have 4 possibilities for the first slot and 4 possibilities for the second slot. But now, of those 4, any 2 that are the same are 0, so we lose 4, so we go right away down to 12. And then, of those 12, the problem is anything that looks like this is linearly connected or linearly dependent on those things that look like this. Right? These two differ only by a factor of -1. So they're not linearly independent. So half of the remaining ones are immediately dependent on the other half. So this reduces it down to 6. So there seems to be a dimensionality of 6 in the vector space that will make up all the antisymmetric tensors. But how do we know it's a vector space? Well, we know that any two members can be added together, and this addition formula is this addition is the same addition as exists in the old tensor product space. And we also know that this guy has a scalar multiplication property in the real numbers, so that's fine. We have the addition, we have a scalar multiplication, right? Every tensor has an opposite tensor, right? This is an antisymmetric tensor, and well, that is the opposite of gamma wedge omega. Now realize I'm putting a negative sign now out in front of this. This is a representative two form, right? This is a representative two form. To be a vector space, you have to have a negative. Well, we just multiply by -1. If you add this to this, you get 0. That's not quite the same as what we were talking about before. It's also true that this equals minus omega wedge gamma, but that's not necessarily the vector space inverse. So just don't confuse those two ideas. And there is always the zero tensor. So we now have a vector space of purely antisymmetric tensors, and it's a subspace. It's a subvector space of the 0-2 general tensor product space. And what are the basis vectors for this thing? Well, the basis vectors are going to be dx mu wedge dx nu. And every member of this vector space is going to be represented by 1/2 omega mu nu. And we know that there's a restriction that omega mu nu equals minus omega nu mu, right? We know about that restriction. And the alternative way of writing this is omega mu nu with these little lines, dx mu dx nu, without the 1/2. And sometimes you'll see a convention that goes like this. You'll see the convention dx mu wedge dx nu equals 1/2 dx mu tensor product dx nu nu minus dx nu tensor product dx mu. Sometimes you'll see this convention, which means there won't be a 1/2 here, right? The 1/2 is sort of absorbed into that definition. So you can see a bunch of different conventions. I think this one is probably the most common, but it's a close call. These two are pretty close. I have seen this one though too. So the vector space of two forms? Let's go back up here. The vector space of all, we called this the vector space of all 0-2 tensors. The vector space of two forms is usually given by a lambda with a 2, and it's called the second exterior power. And then we put the name of the underlying space that it's drawn from, which is the dual space, right? These are forms. So two forms is the dual space, is the operating vector space. I can do all of this, by the way, with the underlying vector space, in which case I'll get things called two vectors, right? And it's the same principle, except now now you would be dealing with things like del mu cross del nu minus partial not del, partial nu tensor product partial mu, right? And that would be partial mu wedge product partial nu. So you can repeat this whole argument for any vector space. You can create this. This is the second exterior power, and you can create the second exterior power of V star, of V, of basically of any vector space. You can create the second exterior power. And the basis vectors, so now let's, with the second exterior power of the dual space, the basis vectors are dx0 wedge dx1, dx0 wedge dx2, dx0 wedge dx3, dx0 wedge, whoops, not x0, dx1 wedge dx2, dx1 wedge dx3, that's 1, 2, 3, 4, 5, dx1, x2, dx1, x3, then dx2 wedge dx3. And these are the basis vectors of this second exterior product. So how do we count these up? Well, if you look at how this works, there are 4 basis vectors, right? dx0 in the underlying vector space, right? This vector space has 4 basis vectors, dx2 and dx3. So there are 4 of those, and I need to pick 2 of them at a time, and I create a basis vector. But it doesn't matter what order I pick them, because if I pick 1 and 0 instead of 0 and 1, I pick 1 and 0, they're really the same basis vector because they're only off by a factor of -1. So I need to pick 2 numbers out of 4 that they have to be different, 2 different numbers out of 4, and it doesn't matter what order it's in. And the mathematical way of doing this is something called, it's a figure called C n pick P, meaning I pick P objects from n distinct objects, and it doesn't matter what order they're in. And CNP equals n factorial over p factorial n minus p factorial, a little famous combinational thing. You may remember from the binomial expansion. It has some version of some exploitation of this from algebra. So the dimensionality of this, the dimensionality of the second exterior power of V star, that's a number, and that number is this, and it's going to actually be C4, 2, where the 4 is the dimensionality of the underlying vector space, which in this case is the dual space of V, and 2 is the it's this n, right? It's we're talking about n forms, right? So in this case we're talking about 2 forms, so that 2 is what lands here in the bottom. And that is going to be 4 factorial over 2 factorial over 4 minus 2 over 2 factorial, which is 4 times 3 times 2 times 1 divided by 2 divided by 2. That cancels and leaves a 2, and you end up with 6. So that is why there are 6 vectors in the dimensionality of 6 in this second exterior power. Now the first exterior power, which is the set of all 1 forms, right? That's going to be the dimensionality of that thing is going to be C4 choose 4 choose 1, which is which is 4, right? It's going to be 4 factorial over 1 factorial over 3 factorial. 4 factorial divided by 3 factorial is 4. And of course, that makes sense because these 4 are the basis vectors of the 1 forms, and the 1 form is literally the covector space. So so that's good, and so now we understand how to count the dimensionality of this vector space. So, but that's a big step, right? We've shown that these guys are the basis of a whole new vector space, and these antisymmetric 0-2 rank tensors form their own vector space. And that's going to become very important as we move on. So now the question is let's get from two forms to higher forms. All right, so now we'll look at three forms. Why not, right? So with the idea of a three form is a three form is definitely going to be an element of a 0-3 tensor product space. And the arbitrary element of a 0-3 tensor product space looks like this. X mu tensor product dx delta. And we want it so that when it operates on a series of vectors, A alpha, partial alpha, B beta, partial beta, C gamma, partial gamma, we want it to be, if we interchange, what we're after is if we interchange any two of these arguments, we want the sign of this to change. We want the sign of the result, the sign of the resulting real number, to change under the interchange of any two arguments. So in order to accomplish that, well, first of all, the straight up multiplication, where this is just an arbitrary element of the tensor product space, is, as you probably remember, it's going to end up being T sub alpha beta gamma A alpha B beta C gamma. That's after you pull out the constant factors, not the constant factors, I should say the scalar factors. Those come out front, and that's where they are. And then what's left is dx mu operating on partial alpha, which of course gives us dx mu partial alpha, which equals the delta function mu alpha. So this mu becomes this alpha, right? So we go through that whole exercise again, but now we have the product of three of these things. So it cleans up all three of these indices, and you end up with that expression. That's just yet again another review of that whole process. So, but now we want this expression ultimately to equal the opposite of any two indices swap. So we want this to be the opposite of T, let's see, beta alpha gamma, and then it would be B beta A alpha C gamma. We want that. And we want it to be the opposite of T alpha gamma beta A alpha C gamma B beta. Now notice the ordering of these guys doesn't really matter, because these are just three real numbers, right? You know, I mean, three scalars. So the scalars are commutative. In fact, all four of these numbers are commutative. It's these indices here that are critical. And the order of these indices can't be changed, because these indices bind with a basis vector of your tensor product space. So these indices have to be carefully ordered. But everything else is fluid. You know, the sequence, whether it's ABC, I could write this all as ABC, but I want the indices to sort of line up in order. But that's just pure convenience, because whether B is here or here, it's still going to sum over exactly the same way, and the sum is completely linear. So, and this has got to equal minus gamma, I think it's alpha gamma beta. Yeah, alpha gamma beta A alpha C. Oh, I did that one. Alpha gamma beta. Oh, it's gamma beta alpha. I need gamma beta alpha, and then it's C gamma B beta A alpha. Now, the problem here, of course, is with 3, you have more interchange possibilities than just 2, right? So I have to account for every interchange possibility. The problem is some of these interchanges are really 2 interchanges, right? So if I take this guy and I still demand complete antisymmetry, if I swap any 2 of these indices, this sign has to go back to positive again. So ultimately, with the same 3 indices, I'm going to get a T beta gamma alpha, B beta C gamma A alpha, and then I'm going to get a T gamma alpha beta C gamma A alpha B beta, and then I'm going to get a T beta gamma alpha. I've already got gamma alpha beta, which will be C gamma A alpha B beta. So now when I have 3 or more, I have the possibility of really recovering the same sign as well. And this is still antisymmetry, because to go from here to here, I flipped 2, but then I flipped another 2. So what I'm basically saying is that the permutation beta gamma alpha, starting with alpha beta gamma, the permutation beta gamma alpha actually requires 2 different interchanges. I have to interchange alpha with gamma and then beta with alpha. So I need 2 interchanges to get this. To get any of these, I only need 1 interchange, right? What's interesting is if I try 3 interchanges, I'm only going to recover the same ones that I had before. So there's now a series of interchanges that are 2, which don't change the sign, because of the antisymmetry drives this, because I do 1 sign change, I get an opposite, I get this negative sign, then I do another sign change, and I get the negative sign twice, so it goes away. So now I need to construct a tensor from the 0,3 rank tensor product space that satisfies this whole behavior. And it's going to be very similar in design to the one we've already done, right? Let me move this over here. And that tensor is going to look like this. It's going to be T mu nu delta times dx mu tensor product dx nu tensor product dx delta, and then it's going to be minus dx, well, why don't I do plus, dx delta tensor product dx mu tensor product dx nu plus dx nu tensor product dx delta tensor product dx mu minus dx mu tensor product dx delta tensor product dx nu minus dx, what do I want next, nu tensor product dx mu tensor product dx delta minus, right, and the last minus will be dx delta tensor product dx nu tensor product dx mu. Phew. Okay, I think I got it. So if I build this 0,3 rank tensor, where these are the basis vectors of a 0,3 rank tensor, but I designed it so that the coefficient, or that the component of this basis vector is the same as the component of this basis vector, is the same as this basis vector, but is the opposite of these 3, then this tensor, when it acts on its 3 vectors, A alpha, partial alpha, B beta, partial beta, C gamma, partial gamma, when this guy acts on this, then guaranteed if I start interchanging these three, I'm going to end up with these exact expressions that I want, which are antisymmetric. Antisymmetric, these 6 different expressions. And now I have a new tensor basis, and this is the new tensor basis. But in order to make it look kind of like what we did before, which I'm going to go back to, where is it here? In the case of the 2 forms, right? I actually wrote it out, right, in terms of the actual basis vectors, and I was able to 0, 1 and 1, 0. I can do that again for these guys, right? And what I'll do is I will move this to another screen and I'll do it. All right, so paste. All right, so there's the, I'll actually shrink it a little bit so I have some more room, right? So now I could write, you know what I think I'm going to do is I'm going to change the thickness of the pen a little bit so I'm not stumbling over myself. Let's try this. So now I have to pick, so I'm going to start with T 0 1 0. Oops. 0 1 2, right? And that's going to equal dx0 tensor product dx1 tensor product dx2 plus dx2 tensor product dx0 tensor product dx1 plus dx2 tensor product dx, oops, I'm sorry, that should be tensor product dx1 tensor product dx2 tensor product dx0 minus dx1 tensor product dx, this is 0, dx2 tensor product dx1 minus dx1 tensor product dx0 tensor product dx2 minus dx2 tensor product dx1 tensor product dx0. So that is, no, I don't want this equal sign, right? I want this. This is one part of the. This is an expression of the components of an element of T03, right? So this is the scalar factor, and these are the components. These are the different basis vectors inside T03, and this is the component of each of these basis vectors in T03. It's going to be the same valued scalar, except these signs are going to drag it into the negative for these particular basis vectors. Now, I can clearly do this again, right? I can do this for T0, 1, 3, and I can do this for T0, 2, 3. Then I can do it for T1, 2, 3, right? But that's all I can do, because if I tried to do it for T2, well, say I tried to do it for well, first of all, if I do it for T0, 0, 0, I immediately end up with the symmetry problem, right? Any two exchanges, T0, 0, 0, is going to always equal minus T0, 0, 0. So all these perfectly diagonal elements must be 0. But what's also true is T0, 0, 1 must equal minus T0, 0, 1, because if I exchange these two, I'm expecting the sign to change. So all of those, anytime you see two of the same number, you're done. It's immediately 0. So all of those don't count. right? All of those don't count. So those go away. And if I tried to do T102, well, that's already accounted for in this mess because the permutation 102 is right here, right? That would be T102, its matching basis vector is dx1, tensor product dx0, tensor product dx2. But we've already got that, right? So we know that T102 equals minus T012, which is we've already done. So it comes up with this sort of the same principle that we only need to do this in the sequence where we only need to write this thing out with the sequence of indices is always increasing. 0 is less than 1, 1 is less than 2. 0 is less than 1, 1 is less than 3. 0 is less than 2, 2 is less than 3. 1 is less than 2 is less than 3. Right? But each one of them is going to be just as unwieldy, well, or I don't know how unwieldy this is, but it's going to be just as long as this. Every one of these is going to have something that looks like this right next to it. And that large something is again going to comprise a basis of another vector space, which we're going to call the third exterior power of the dual space. And the number of vectors, well, we see we've got 4, right? We've counted 1, 2, 3, 4 basis vectors. So if that's right, then C4, 3, which is 4 factorial over 3 factorial times 4 minus 3 factorial, which is 4 factorial over 3 factorial is just 4. 4 minus 3 is 1 factorial, so it equals 4. So we've got the right number of basis vectors based on our theory before. And so now we've created another vector space, and this is the vector space of 3 forms, and it is a subvector space of all 0-3 tensors. You can add them, you can subtract them from each other. However, you can, again, remembering that the second exterior power and the third exterior power are just as different vector spaces as T2 is different from 0-3. They're totally different vector spaces. So you cannot add, you can never write something like alpha wedge beta plus gamma wedge delta wedge, well, I'll say alpha again, doesn't matter, right? You can never do that. But, so we've created yet a third vector space. And this third vector space still has all these key properties, right? Alpha, wedge, beta. It's associative, so it's alpha, wedge, beta, but alpha, wedge, alpha is 0. So this equals 0. So anytime there are any 2 in here that are the same, you're going to get 0. And you can figure this out by just doing alpha mu dx mu wedge alpha mu dx mu wedge beta b beta dx beta, and you just work that out. You work it out in terms of these tensor products, and you'll see that these things are going to start to cancel, and until they're all 0. So anytime you have a duplication in this process, you're going to end up with a 0. And from this process, we can just keep taking 1 forms. Remember, every one of these is a 1 form, right? And we can keep taking 1 forms, and we can make now, what happens if we make alpha, wedge, beta, wedge, gamma, wedge, delta, right? What if we did that? And we would end up with, say, A mu, B nu, C, oh God, I'm running out of darn letters here. Let me just, I guess I'll just, these guys are going to be replaced with their component forms, right? So the component forms will be A alpha dx alpha, B beta dx beta, C gamma dx gamma, and d delta dx delta. And when we do that, we're going to end up with alpha, A alpha, B beta, C gamma, D delta, dx alpha, wedge, dx beta, wedge, dx gamma, wedge, dx delta. And now, in this circumstance, something very interesting is going to happen. When I start to calculate the general, so this now is the fourth exterior power of V star, right? And when I start to calculate these components, something very important and interesting is going to happen. I'm going to discover that the general tensor for this has got to be 0, 1, 2, 3, right? Because I have 4 indices in this thing. And there's no additional permutations, right? There's no other way, any other permutation of this, t, say, 0, 2, 1, 3, is going to be eaten up in one of the tensor product sequences that live inside this big combination, right? And so there's no other permutations. There's only one. There's only one basis vector. There's only one basis vector, which of course makes perfect sense. It's C4, choose 4, right? Which is 4 factorial over 4 factorial times 0 factorial, which is 1. Because, of course, 0 factorial equals 1, right? So, so we're at one dimension. We're in one dimension now. So the fourth exterior power actually has one dimension. So we started with the first exterior power, which had 4 dimensions. We went to the second exterior power, which had 6 dimensions. We went to the third exterior power, which had 4 dimensions again. And then we're at the fourth exterior power, which has 1 dimension. And by the way, the 0th exterior power, right, that is just the those constants. So it's in the sequence. So we're going to see that this is actually pretty important. This guy, it's always true, it's going to always be true that the nth exterior power of a vector space with n dimensions is always going to have always going to be one-dimensional. So that's always true. And it's always true that there's going to be a low exterior power whose dimensionality exactly matches one of the larger exterior powers. So the fact that this 4 is the same as this 4, we're going to see in another lecture, is really, it's always true. It's always going to be true. And that's because this is always true, right? C, I think the way it goes is Cn of P is always going to equal Cn of n minus P. And the reason that is what this is n factorial, P factorial, n minus P factorial. But that's going to equal n factorial of n minus P factorial times n n minus P factorial, which of course equals n factorial over n minus P factorial, n minus n plus P over P factorial, right? So these two are the same. So that's always an important fact, because it establishes what we're going to call a dual relationship between these two vector spaces. And so what we've done is we've introduced this concept of, I'm going to go back to my slightly thicker pen here. We've introduced this context of the vector product of two one-forms, dx1, dx mu, dx nu. And we've shown that we can string this vector product along as many times as we want, dx delta. However, once we, I guess I should point out, if say we've gone all the way up to 4, x mu, nu, delta, dx gamma. What if we add one more, dx beta, like that? Well, now we're going to be dealing with 1, 2, 3, 4, and I'm going to have to fill in this slot. I'm going to have to fill it in with one of these other numbers, like say 2. And now I'm going to end up with dx0, dx1, dx2, dx3, say dx2. Well, now I have 2 of the same one forms buried in my wedge product, which means this thing's going to be 0. And that's always true. Whenever I'm trying to make a P form where P is greater than the dimensionality of the underlying vector space, I'm going to always get 0. The vector space is going to be totally trivial. It's going to be 0. So the 5th exterior power of our 4-dimensional tensor product space is just the single set 0, right? And there's nothing, and all greater powers as well. We showed before that minus a one-form wedge with a one-form, we have this relationship, right? And that's always true, right? So it's going to be true that gamma wedge omega wedge delta, if I do one switch, I'm always going to get the opposite of, it's going to be gamma wedge delta wedge omega. So this antisymmetry is always true for any length of wedge products. So a single interchange of the wedge product ordering is going to change the sign of the overall wedge product. And if I do it twice, I'll recover the sign. So if I flip 2 more, well, if I flip these two, flipping 2 and 2 back doesn't help. But if I go then delta wedge gamma wedge omega, then the minus sign would come back. So we've introduced this wedge product. We've discovered the different exterior power vector spaces, right? We've discovered these vector spaces. And for our space-time, we have 4 of them. And we actually have 5 because we do have the D0 of V star, which is just all these functions. It's just functions on the space-time, right? And again, that is still a vector space of dimension 1, right? There, because it's just it's just the bin of the real numbers really at any point, and it'll be functions on the entire space-time when we talk about it as in terms of form fields. This one had dimensionality 4, this one had dimensionality 6, this one had dimensionality 4, and then this one had dimensionality of 1. So we've introduced those. We've shown that they're vector spaces because they're all subspaces of their associated tensor product space. And we've discussed in detail the antisymmetry properties of this thing. And we've shown that there's a constraint on the components such that the interchange of any 2 components will change the sign of the component. And if you have an even number of interchanges, you will change the sign. You won't change the sign. The sign will change and then change back an even number of times. But if there's an odd number of interchanges, 1, 3, or 5, you will change the sign from positive to negative, or vice versa. And so that is basically the structure of how the wedge product works in the most rote and straight-up way. In our next lecture, we're going to start expanding on how to understand the significance of antisymmetric tensors. We need to know why does antisymmetry, why is that so important? What's the motivation for doing this? Why bother creating spaces that look like this? Why bother? And that's the subject of our next lecture.